All right, as we get started today, this will be our last lesson for a little while recording. So, Gavin, you'll be going back to the older recordings with your former classmates as opposed to your current classmates. Anyway, we're going to start with the practice exercise today. Practice exercise 31. You may use your calculators. You've got some fractions. You've got some mixed numbers. You're converting all of it into decimals if necessary. It says round to the nearest thousandth. How many decimal places is that? 3,000. Tenths, hundredths, thousandths. All right, so anyway, hopefully that little tidbit helps you there. Go ahead and begin. First person to finish, stand where you're at, keep track of the numbers. What number are we on? 4. All right, let's go and stop where we're at here. So I think Adam was first, right? Second was Brandon. Third was Dylan. Fourth was Michael. Fifth was Brecken. And sixth was Lon. Okay. Check your answers. The first one we could have done without a calculator. How many plugged it in and is like, oh, duh? How many realized before you plugged it in, I got this? Yeah, what is the first one there, Adam?
0.798.
0.798, right? It's already thousandths place. The next one is one we should have remembered from our junior high days, Adam.
Okay, 0.79. That's what I said about remember.
For 5/8? Well, you could have used your calculator for it. Let's see, let's go to Brandon. What did you get for the second one?
0.25.
0.625 is correct. I assume you had 0.798 for the first. The next one is also something we should have remembered from our junior high days, Brandon. 29.75. Now that next one, definitely not learned that one. Just plug it into the calculator because a fraction of our class means divide. So you just divide 69 by 217, we get 0.318 when we round. For the next one, that's another one we should have remembered from our junior high days, Brandon. 89.125 is your 1/8. The next one we could have done without a calculator, certainly. And what do we have? Just 0.25. That was easy enough. On the bottom row, that first one on the bottom row, we are very thankful for a calculator.
0.049.
0.049 when we round to the thousandths place. The next one we all should have been able to do without a calculator. This is an easy one to remember from our junior high days and elementary days even.
103.5.
103.5. The next one, back to being thankful for a calculator.
0.511.
0.511. The next one we could do without a calculator.
0.029.
All right, so third was Dylan. Are you good so far? All right, what did you get? 0.0284 initially, but since it said to round to the thousandths place, 0.028. Remember, a 4 is not big enough to bump it to a 9. So 0.028, or if you left 0.0284, I'd give that to you because, well, if necessary, round. It's not necessary to round. All I need is 4 digits after the decimal. 5/6 is another one we memorized when we were in junior high. 0.833, but we're rounding to the thousandths. And then 1/9 is another one we memorized in junior high. 0.111, it keeps on going with ones and so on and so forth. But 0.111 our answer. Anyone else get them all correct, just not as fast as Dylan?
Well, unless you count that one.
No, the 0.0824 I'll give you. I'll give you that one as is. Questions on any of these? All right, now, one thing I want to show you on your calculators, and again, those are the TI-30XA. You've got an obvious advantage here because I can show this to you. I think, Gavin, you do also. On your calculator, if you look right above the decimal point, you should see the word fix. Fix allows you to have the calculator do all of your rounding for you. So if you were to use the second function, hit the fix button, and then tap a 3, second fix 3, you'll notice your calculator goes to 3 digits, 3 decimal places. So do that. Second fix 3. And you'll notice there's 3 digits on your decimal. If you were to do something like, I don't know, 8 divided by 7, well, that comes out to a really long decimal, but if you've got the fix on, it'll round to the 3 decimal places for you. You don't even have to think about 5 or greater, bump it up, 4 or smaller, fall off. It does all of it for you. So the fix is kind of a neat feature. If there's a set number of decimal places, like here it was thousandths, what if it said round to the nearest hundredth class? You'd fix it to 2 decimal places. So you can leave the number on the screen, second fix 2, and notice now it'll round to the second decimal. What if I wanted 5 digits after the decimal? Second fix 5, and all of a sudden now it shows you the 5 digits after the decimal point. So it can do all of that for you. If you have the TI-30X2S, it also has the fix. When you do second fix, it'll bring up a whole row of digits that you could choose. F stands for floating, means the decimal goes where it belongs. 0 places means whole number, 1, 2, 3, 4, and so forth. You would use the arrow keys on your calculator to scroll over, so I can arrow over to the 3, and then when I hit enter, from this point forward, for instance, 8 divided by 7, it'll round everything off to those 3 digits as well. If you have something other than a TI-30X, then, I don't know, kind of on your own as far as how to set the fix on the calculator. Did you figure it out already on yours?
I figured out a process.
Okay, that works too. All right, any questions on this exercise, converting fractions to decimals? Obviously, you can go faster if you remember certain ones from junior high. All right, go ahead and pass those in if you would, please, and have your notebooks out. Keep them closed on your desk for now. Notebooks out, keep them closed on your desk for now. I want to review some things we've been talking about recently. Obviously, a lot lately we've been working on getting triangles congruent. We've got 8 ways now to prove triangles congruent. 4 of those ways work for any 2 triangles. 4 of those ways are right triangle specific. And let's go to Lana. Can you remember the 8 ways to prove triangles congruent?
The 2 new ones is like HL.
Let's just give the all 8 ways. Just go. So you said hypotenuse leg. That's for right triangles, of course. That's our newest.
HA.
Hypotenuse angle is our next newest. Leg is our oldest right triangle method.
Angle.
And leg angle, which originally again meant adjacent acute angle, now could mean either acute angle. So.
And then SAS.
So our first.
ASA.
Second.
SSA.
Third and the
then-
most recent.
Is it SSA?
It is not SSA. That
Is
is
it?
not a way to prove triangles congruent. We're going to show why not here in a little bit. Not today, but moving forward, we'll show why you cannot use side-to-side angle. The way my math teacher told me, though, just to remember is, if you look at it backwards, it's a bad word, and we don't do that here. So don't use side-to-side angle to prove triangles congruent. Don't do it, young person. But what is that last way? Dylan? Side angle
Oh,
angle.
yeah.
Side angle is our last way of proving triangles congruent. So those are our 8 ways to prove triangles congruent. So we finally completed the poster at long last. We've got them all. And for those of you who are like, oh, you know, I never really noticed that was crossed out before. Yeah, it is. All right, so anyway,
That's pretty
put this
smart.
back up in the, put that back up on the wall. All right, we'll worry about the other poster here in a little bit. We also talked quite a bit about, wherever I put my chalk, put it down over there. We also talked quite a bit about an isosceles triangle. And of course, there's some clang just in knowing two sides are equal, class. Equal angles opposite those equal sides. But we said this specifically. In an isosceles triangle, if you draw this line right here, if I know that it bisects the vertex angle, what other two things do I know about this line? Josh?
Perpendicular to the base.
It'll be perpendicular to the base and
Bisects the base.
it's going to bisect the base. I also said if I draw this line and I know that it bisects the base, there's two other things I know about that line, Michael.
It's perpendicular to the base.
Perpendicular to the base and
Bisects the angle.
bisects the vertex angle. I said if I draw a line in an isosceles triangle like this so that it is perpendicular to the base, there's two other things I know about this picture, Brecken.
The bottom lines.
That it'll bisect the base
Bisects the top angle.
and it'll bisect the vertex angle. There we go. So you know 3 things. Given any one of them, you'll know the other 2. We've proven it all 3 ways now. We also, yesterday, began talking about not a triangle with 2 equal sides, clang equal sides, equal angles, or clang equal angles, class, equal sides. But I said, no, what if instead of having equal sides, I have unequal sides? What's the clang response to unequal sides? Let's just call this triangle X, Q, J, because those are some letters that don't get used often enough. Adam? If I know that JQ is bigger than XJ, what else do I know?
The angle X is bigger than angle Q.
Then I know that angle X, which is across from the big side, is bigger than angle Q across from the little side. Good. What if I had a triangle and I knew that this angle, let's just call it M, is bigger than this angle P? I know that M is bigger than P. What else do I know, Noah? If I'm given that angle M is bigger than angle P, what else do I know? What's the clang response to, in a triangle, having 2 angles that are not equal? Okay, which sides? MN is big, and other way around. Big angle, big side, little angle, little side. Other way around. Okay, so big angle has across from it a big side, little angle across from it a little side. Then we said this, that if you were to have any given point, any given line, there's an infinite number of lines you can draw from that point to that line. But the shortest line, Abby, will always be the perpendicular. And therefore, if we know that a line is the shortest from a point to a line, well, then we know that that shortest line class is the perpendicular. Perpendicular is the shortest. If it's the shortest, then it's perpendicular. We looked at that as well yesterday. Last night for homework, you copied theorems 15 through 18 and their corollaries. Go and open up to the theorems corollaries section. Go and open up to the theorems corollaries section. And let's have, see, Brecken, if you'll read theorem 15 for us nice and loud. Theorem 15.
If 2 straight lines drawn from a point in a perpendicular to a given line cut off equal segments from the foot of the perpendicular, then
Read that again for us if you would. Joshua, nice and loud.
If two straight lines drawn from a point and a perpendicular to a given line cut off equal segments from the foot of the perpendicular, then the straight line that cuts off the greater segment.
Theorem 15? Are you reading
Oh,
Theorem
I
15?
was on corollary.
Yeah, sorry, Theorem 15.
I
Read
saw
that for us.
15. If two straight lines drawn from a point and a perpendicular to a given line cut off equal segments from the foot of the perpendicular, then they are equal.
All right. Now, pardon the English class here, but do you see how that's kind of a, what are we talking about? You kind of read it, it's like, what? Underline, if two straight lines, mark that as your subject. And your verb is cut. If two straight lines, blah, 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 cut off equal segments. That's the subject and verb. Do you see we've got that participial phrase that's in the middle that just seems wordy and confusing? Drawn from any point in a perpendicular to a given line. All of that is just kind of describing the two straight lines. So here's the bottom line. We have a perpendicular. Don't draw this yet, you'll do it in a minute. We have a perpendicular. The theorem says if you pick any point in this perpendicular, and if you draw two straight lines from a point in a perpendicular to a given line, okay, so you draw a couple of lines, here's a line, there's a line. If you draw two straight lines from a point in a perpendicular to a given line, if these two straight lines cut off equal segments, there's your direct object, from the foot of the perpendicular. That's what this point here is. That's called the foot of the perpendicular. It's where the perpendicular meets the line. If we draw two lines from this point, if they cut off equal segments, then the lines have to be equal in order to cut off equal segments. That's what it's saying. This is where grammar class helps, right? Finding, identifying verbal phrases and spitting it out. If two lines are cut off equal segments, then they're going to be equal to each other. Turn over, if you would, to the proofs of theorems corollaries section at the top of a new sheet of paper, Theorem 15. From a point in a perpendicular, two lines cut off equal segments. Therefore, they are equal. That's how we're going to kind of shorthand this. From a point of perpendicular, two lines cut off equal segments. Therefore, they are equal. If you would, go ahead and draw a line, call it AB. Draw a perpendicular. Call it XY. Or we'll allow Y to be the foot of the perpendicular. Pick a random point in XY. I don't know, right here looks good. Call it P. Draw any line from P down to AB. And then on the other side of the perpendicular, draw another line from P down to AB. We'll call these points of intersection M and N. We want to prove that if these two segments are equal, then the lines are equal. So given XY is perpendicular to AB. That was the first thing we drew. Notice we drew a perpendicular. Then we plotted a point called P. So P is any point in XY. P isn't a special point. It's not necessarily the midpoint or anything like that, though it actually kind of looks like the midpoint. I didn't do a good job picking that. But P is any random point in XY. And then we drew two lines, correct? We drew PM and PN. PM and PN are drawn so that, whether it looks like it or not, MY equals NY. From a point perpendicular, two straight lines cut off equal segments from the foot of the perpendicular. We want to prove then that these two lines which do the cutting, PM and PN, are equal. this out of your way. Well, once you have that down, 2 columns, statements and reasons. Can copy down your first statement and your first reason. And let's see, eeny, meeny, miny, you who dropped pencil. Brecken, thoughts? I want to prove that PM and PN are equal lines.
Can you remember the angles on the side?
Sure. So we could call these 1, 2, 3, 4, 5, 6. You did not want the 2 angles on the outsides? Okay. So we'll number our angles. I went 1, 2 at the vertex, 3, 4, 5, 6 across the base. He said he wanted all the angles that were inside the triangles that were formed by these lines drawn from the point in the perpendicular. All right? Brecken, thoughts?
4 and 5 are right angles.
All right, we have a perpendicular plane. That means we have right angles. Angle 4 and angle 5 are right angles. Reason?
Definition of perpendicular.
All right. Lana, thoughts next. We got a couple of right angles here. Other thoughts on some things that might help us get PM and PN to be equal? What are my 2 major ways to prove lines are equal to each other?
The equal sign. Wait.
I can prove lines are equal if... Josh?
Is it get the triangles congruent and then use CPCT?
That's a great one. If the 2 lines are on 2 different triangles, get congruent triangles, use CPCTE. Are these 2 lines lined into different triangles? Yes. Okay, so that's a valid option. What was the other way to prove lines equal, Adam?
To have equal opposite wait.
Yeah, if in the same triangle their opposite angles were equal. Lana, are these 2 lines in the same triangle?
No. Or
Yes, they are, aren't they? If you kind of ignore the middle line here, they would be in the same triangle. So if I could get opposite equal angles, then I would get opposite sides. So either of those is available to me, either congruent triangle CPCTE or try to get the opposite angles 3 and 6 to be equal to each other. Either of those work. Lana, your thoughts now.
then you'd have to use one of the angles then. So like, would it be 2 and 30?
What about 2 and 3?
Like sides opposite. Or angles opposite. Some forget how you do the reason.
Brandon, helper?
So we already have my equals my, so now we're going to say py equals py, and then we already have congruent triangles.
Okay, so you said to say py equals py,
Oh.
and reason for py equals py?
Identity.
Identity. And you say that gives me congruent triangles? How so?
No, we have a side and a side.
We do. So I see sides right here equal, and I have sides right here equal. Where are the angles that are equal?
Two right angles. The four.
Oh, well, I haven't said they're equal yet. Oh.
There you go. Then.
So number 4, go ahead and say,
Angle 4 equals angle 5 because all right angles are equal.
all right, so you said there's some angles. So now I could say,
Triangle MYP is congruent to NYP.
triangle MYP is congruent to triangle NYP. Because why?
Side angle side.
Side, angle, side. Here's some sides, here's some angles, here's some sides. As an alternative, we could have said that because we have right angles, we have right triangles. And if we said right triangles class, instead of side, angle, side, we would have said leg. Good, Noah. And that would have gotten the congruent triangles. The point is, this triangle and that triangle, they congruent, so therefore, Lana, what is true? Back to you.
So would it be like or PMY or PNY? Wait, no, it would no.
What are we trying to prove again, Lana?
That they're equal.
What are equal?
PM and PN,
PM and PN. And how do we say we wanted to get those two lines equal?
like congruent triangles or something.
Well, I've got congruent triangles. So if those two triangles are congruent,
CPCT.
they're equal by CPCTE. There we go. PM equals PN by CPCTE. And we're done. Pretty straightforward.
I always like psych myself out.
Don't psych yourself out. All right. So there we go. Pretty easy, straightforward proof there on Theorem 15. Questions on Theorem 15. Corollary 15-1. So once you finish copying that down, turn back to Theorems Corollaries section. And Corollary 15-1. Let's have Noah read it nice and loud once you find it so the camera can hear you.
If two straight lines drawn from a point and perpendicular to a given line cut off unequal segments from the foot of the perpendicular, then the straight line that cuts off the greater segment is the greater straight line.
Okay, there we go. Kind of floundered there at the end a little bit. We got it out. Abby, would you also read it for us nice and loud so the camera can hear you?
If two straight lines drawn from a point and a perpendicular to a given line cut off unequal segments from the foot of the perpendicular, then the straight line that cuts off the greater segment is the greater straight line.
All right, this is like Theorem 15. From a point of perpendicular, two lines cut off unequal segments, though. And it says if they cut off unequal segments, they're not going to be equal, they're going to be unequal. The bigger segment will be cut off by the bigger straight line. So what it's saying is if it cuts off a big segment here, then this line has to be a bigger line than that one. Does that make sense? Go ahead and turn to back to the proofs section then. And on the back side of Theorem 15, Corollary 15-1, from a point of perpendicular, two lines cut off unequal segments. Therefore, the greater segment is cut off by the greater straight line. From a point of perpendicular, two lines cut off unequal segments. Therefore, the greater segment is cut off by the greater straight line. Go ahead and draw a line, AB. Draw what appears to be a perpendicular to it, call it CD. Pick a random point in CD, call it E. Pick a random point in CD, call it E. From E, cut off a segment, DF. Then on the other side, let's see, do we want to go bigger the second time or smaller the second time? Brandon?
Let's go bigger.
Bigger. All right, so see how big DF is? Cut off something bigger than DF the second time through. and call this EG. So that we have a little segment DF and a big segment DG. And we are given CD's parallel to AB. E is any point in CD. EF and EG are drawn so that FD is smaller than DG. FD's little, DG's big. We want to prove that the line that cuts off the little segment is the little line, and the line that cuts off the big segment is the big line. What am I trying to prove here, Noah? Want to prove if you have unequal segments, whichever line cuts off the big segment is the bigger line. So I'm trying to prove specifically in this picture that EG is bigger than EF. I want to prove that EG is bigger than EF. The line that cuts off the bigger segment is the bigger line. And again, there are those who say, well, duh, obvious. Well, is it obvious though? No? It makes sense at least. It looks like, yeah, I could definitely see that. If it cuts off the bigger segment, it's got to be bigger, but we need to prove that it's the case. So your statement's reasons, get that first statement and reason down. At this time, I'm not trying to prove lines are equal. I'm trying to prove lines are not equal. We don't have a lot of thoughts for lines being not equal, do we? What have we recently proved, though, about lines being not equal? Dylan? If in a triangle, the angles are not equal, correct? I'm going to number this angle 1, I'm going to call this angle 2. Do you see that EFG is one big triangle? And we ultimately want to prove EG big, EF small. What would have to be true in the entire triangle FGE for EF to be small and EG to be big? Joshua?
The perpendiculars.
Okay, ignore the perpendicular.
Yeah.
Look at the triangle. I want EF to be little, EG to be big. What would give me unequal sides in a triangle, per yesterday?
Unequal.
Unequal angles. Which angles specifically would need to be unequal and how?
F and G.
Or rather 1 and 2, since there's
Well,
two angles
yeah.
in F and 2 at G. Okay, who needs to be the big angle, who needs to be the little angle?
G, well, 2 needs to be big, and then F needs to be small.
So across from the little side, we need a big angle, and across from the big side, we need a little angle?
Oh, no. It's just the way that sorry. 2 needs to be small, and 1 needs to be big.
There we go. I want 1 to be the big angle. I want 2 to be the small angle. I want 2 smaller than 1. Does everyone see that now? If 2 is little and 1 is big, then in this triangle, this side's big, that side's little. I've got what I want to prove. So we're kind of ignoring the perpendiculars. We discussed the triangle. However, somehow, some way, we're going to use that perpendicular fact to get angle 2 and angle 1 to be unequal? Now this is a corollary. A corollary is a statement, class, that you can easily prove using the previous theorem. But the previous theorem didn't even talk about unequals, did it? The previous theorem said that if you got two lines drawn from a point of perpendicular and they cut off equal segments. Do I have equal segments? So now am I supposed to use this theorem to prove the corollary?
You don't.
Then why is it a corollary?
I don't know.
Oh. Well, maybe we do. Remember I said a lot of times when things are not equal, mark off equal quantities. Get equals. If DG is big, then that means I could fit DF on DG with room to spare, correct? I could measure this length and I could mark it off somewhere, maybe right about here at a point called X. Let's do that. Number 2, locate X on DG so that DX equals DF. And this is based on the definition of equal line segments. Line segments whose endpoints can be made to coincide. So DF and DX will be equal segments. So far, so good? And since DG is bigger, we know DG has room for this point X. But remember, the theorem said if lines are drawn cutting off equal segments. Well, here I have a line that cuts off this segment. I don't have a line that cuts off this segment, so thoughts? Draw CX. What do you suppose the reason would be? Only one straight line may be drawn between 2 points, or 2 points determine a straight line. And now all of a sudden, class, if, back to the theorem, if from a point of perpendicular, lines are drawn cutting off equal segments from the foot of the perpendicular, then the lines are equal. So just like that, I know what about CX? They're equal?
It's equal to CC.
CX has to equal CF.
Is it C or is it E?
Oh, E, I'm sorry. Sorry, not E.
Yeah.
Sorry, C is way up there. E is the point. Sorry, thank you. Draw EX, thank you. And EX equals EF. There we go. Sorry, thank you. I was just seeing if anyone was paying attention. Well done. All right. EX equals EF because if from a point in a perpendicular lines are drawn that cut off equal segments from the foot of the perpendicular, then the lines are equal. Ugh. It is a lot to write. So that means that line and that line, they equal.
Mine does not look very good.
Does not look very equal. That's okay, we don't trust our eyes. It's equal anyway. Even if it doesn't look good to your eyes. It's like when Renee draws me a picture and say, well, that's very nice. Is that an elephant? No, it's a, what was it she drew? I don't even know. Maybe it was supposed to be a dog. I don't know, but I'm like, it looks like an elephant. What's a dog? She's got this whole you don't trust your eyes thing figured out. You know what I'm saying? Brandon, thoughts, question?
No, what is that word after
Foot, FT.
Oh.
It's an abbreviation from years ago. Foot, from the foot of the perpendicular. Sorry, I stole the abbreviation for 1 foot equals 12 inches. Like, I don't need to teach you that when you heard that one when you were younger. So, all right, now I'm looking at this and I'm like, equal lines, clang, class, equal angles. Looking at triangle, not C, E F X, if X. Yes. Yeah, let's number this angle right here, angle EXF. Let's label it angle 3, class. We know angle 1 equals angle 3. Because, Brecken,
Angles opposite, angles sides, interchangeable.
so I know 1 and 3 are equal. Well, we took the suggestion. It was a corollary, so we used the old theorem, but we're done with that now. We got our clang. How does that help me to get EG greater than EF? Or better yet, how does it help me to get angle 2 is smaller than angle 1? Because remember, if angle 2 is little and angle 1 is big, the side across from angle 1, which is EG, is going to be big, and the side across from angle 2, EF, is going to be small. How does getting 1 equal to 3 help me to get 2 smaller than 1? Adam?
You could say that, you could say something to the point of where, like, you could substitute, the EDX with the F, with the EX.
EDX, you're talking about this angle right here?
Or you could say something to the point of how EDG is greater than. How could you say that?
I don't know, because I'm not quite sure what you're trying to say. Are you trying to say that triangle EDG is bigger than triangle EDF?
Something like that.
Something like that? We couldn't say that yet. I mean, in about 5 months we
But
could.
Did you say, like, oh, we haven't come with that stuff yet?
No, we haven't done anything with areas. Because to say a triangle is bigger than another triangle, you have to know something about the area. We haven't done anything with areas yet this
Maybe
year.
we should do that right now.
No, we can't. We're not ready.
Ready.
Okay, let me put it this way to you, class. At the very bottom of the proof, which I don't have a whole lot of space, so hopefully this fits. I'll write small. I need to say that EG is bigger than EF. We all agree, right? And we said probably the most likely way to get EG to be bigger than EF is to get angle 2 smaller than angle 1, correct? So somehow, although I'm here, I need to get here. I know that 1's equal to 3. I need 2 to be smaller than 1. Adam?
We have to find a way to say that 2 is larger than 3. Or no, 2 is smaller than 3.
Do you see that if, class, 2 were smaller than 3, then I could do a substitution? So now the question is there a way to get 2 smaller than 3? Abby's nodding her head. Abby?
Well, I have a way, but it's really long.
What's your long way, Abby?
Like, you could state that CDX is a right triangle.
Okay, CDX is a right triangle. That's true. Okay, so that's this triangle here.
You'd have to number the angles and see.
Let me call this 4 and 5.
Yeah, and you could say that 3 and 4 equals a right angle.
Okay.
And then if you number the other angle, let's see.
Call this, what are we at, 6?
You could say that C equals, is that 4 and 6?
This angle at E equals 4 plus 6.
Oh, that's E? Okay.
Yeah, I got that confused too. C is the random point up here, and then E is this specific
Okay.
point.
And then angle 2 plus angle E equals a right angle.
Okay, so angle 3 and 4 are complementary, and 2 and 4 plus 6 are complementary.
And then you could, where was I going with this?
And complementary means they add up to a,
Right angle.
or better yet, we could say if angles are complementary to the same angle, they're
Complementary to each other. Oh,
equal to each other. So since 3 is the complement of 4, and no, because that's 2 is the complement of 4 plus 6.
But if C equals 6, and the wall is greater than any of its parts. I haven't quite very covered.
Her way actually would work if we could rig it right. We could probably make that work actually. So I don't think you're on a wrong track. You're on a long track. But I was curious to see what your thought was, and it's not wrong. It's just hard to put together. But it's not a wrong line of thought. Someone else have a maybe less convoluted way to get 2 small and 3 big. Let me erase some of these. A way to get 3 to be bigger than 2.
Can you do like a subtraction thing?
Because does everyone see if 3 is bigger than 2, then by substitution 1 is bigger than 2, and then I've got big angle, big side, little angle, little side. All of us see this. This is what the proof comes down to, is somehow getting this angle 3 to be big, and this angle 2 to be smaller. Reckon?
Oh, never mind. I'm thinking something.
Okay, we won't call him Reckon.
Don't go.
Josh? Adam?
Could you say that 3 is the exterior angle of the triangle?
3 is exterior to this triangle. 2 is an opposite interior. And we know that, number 6, an exterior angle of a triangle is greater than either opposite interior angle. Therefore, number 7, by substitution, angle 2 is greater than angle 1. And then number 8, because we have unequal angles in a triangle, we have unequal sides. So in a triangle, side opposite greater angle is greater than side opposite smaller angle. And there we go. It all came down to using an exterior angle.
I was just thinking that.
And that's why I was marking that triangle. Abby was looking at the wrong triangle there. Not wrong, but not the one that would make it easiest. So I was trying to direct your attention. Look at that side triangle and notice that 3 is exterior to it. Questions on Corollary 15.1 proof. In a triangle, side opposite greater angle is greater than side opposite smaller angle. Quickly turn back to theorems corollaries section. We do need to finish out this material very quickly, so I'm going to keep you a little bit past the bell because we're syncing this up with videos that were pre-recorded a couple of years ago. Turn back to theorems corollary section. Look at theorem 16. We have a converse statement. Theorem 16. You can finish copying later. Theorem 16 says this: if 2 straight lines drawn from a point perpendicular to a given line are equal, then they cut off equal segments. Follow with me here very quickly. We have a point perpendicular. We draw a line. We measure with our compass. We measure an equal length here. If these lines are equal, so says the theorem, then the segments have to be equal. Well, think about it. If these lines are equal, and this line equals itself, and it's a perpendicular, then we have right triangles, hypotenuse, leg, they're congruent, CPCTE. Easy enough? Corollary 16-11 says, if from a point in a perpendicular, you draw lines that aren't equal. You draw a line, measure it, and then maybe you go shorter. You shrink the compass a little bit and measure off a shorter line so that this is big and this is small. We would do the same thing. We would take the small measurement and mark it here so that we have equal sides here. That would give us equal angles. Hold that thought. Then the greater straight line cuts off a greater segment. So if this is a smaller line, the fact that we could make equal segments here, the whole is greater than any of its parts, therefore this whole is greater than that one. So a greater line is going to cut off a greater piece, a smaller line, a smaller piece. And that's the gist of what we would do for corollary 16-1. Questions on all of that? Nice thing is it's pretty intuitive, isn't it? If you have equal lines, they're going to cut off equal segments. If you have lines that cut off equal segments, they're going to be equal lines. If you have a line that cuts off a big segment, it's a big line, little segment, little line. Little line, little segment, big line, big segment. Pretty intuitive stuff. So not stuff that should be particularly confusing. For homework this evening, you're going to do handout number 17. Handout number 17. Obviously, you guys in the classroom don't have to worry about the fact that it's number 17. Gavin does. Okay, so you'll just do the handout that I give you. It's a proof that can be done in 6 steps or it can be done in 7 steps. Just depends on the way you want to do it. There's room for an optional 7th step. And I'm only giving you one thing, that right at statement 4, you're going to want to make the statement that angle A is bigger than angle B. You figure out how to work up to it and how to build off of it. So you're doing almost the entire proof on your own. Gavin, it's been good recording some lessons fresh and new for you. We'll be back in a few weeks for just a couple of lessons that also need to be re-recorded. Otherwise, trust that the old lessons that were recorded a couple of years ago will still work well for you. All right, you are dismissed. Have a wonderful rest of your day.